Chapter 5, Lesson 3, Triangle Side and Angle Inequalities. Open your book and let's get started. So we have Theorem 13. If two sides of a triangle are unequal, the angles opposite of them are unequal in the same order. And then Theorem 14 is saying the same words except it's flipping sides and angles. So it says if two angles of a triangle are unequal, the sides opposite them are unequal in the same order. So they are the converse of each other, and we'll explore more what this means. So this is basically saying that, let's take, for example, the equilateral triangle. So every angle, let's say 60, is across from the size of 5. That's the length of this side. And so this 60-degree angle is across from a 5, and this 60-degree angle is across from a 5. So this equilateral triangle has sides that are 5 on each side, and therefore they're equal. But here's the difference. Isosceles has 75-degree angles in 2 of the corners and 30-degree angle on the other. Now, 75 is diagonal or going across from a size 7 side, and 75 degrees is across from a 7, but 30 degrees is across from a 4. So what this is showing us, these theorems, is that however large the degrees are, the side that goes across from it will also correlate, being large or small. So since 30 degrees is the smallest angle in this triangle, it's across from the smallest side in the triangle. And then scaling, you can see this the best. So 15 degrees is the smallest degree of corner. And then we have across from the 3. And then 40 degrees is across from 6. And 125 is across from 8. Here's some more examples. So we have 90 degrees is our largest angle, and it's across from the largest side. Here's another one. This one's an isosceles because we have 38 degrees across from a size 4 side, 38 degrees across from a size 4, that makes sense, and then 104 is across from 6, the longest side. The largest degrees, the largest side. Here's another isosceles triangle, and here's an equilateral triangle. We're going to go over a proof that Euclid would like us to go over. So this is in your book on page 196. Follow along with the video. Okay, we're going to work on page 196 with this theorem right here. So Theorem 13 says, if two sides of a triangle are equal, the angles opposite them are unequal in the same order. Okay, so we are going to go through this problem together. So the first part says we have a triangle that is, we're going to use this larger triangle actually. Let me move this down. We have a triangle A, B, C, and they want us to know that this triangle A, B, C is with BC, this line segment right here, and that BC is greater than AC. And we would like to prove, our job is to prove that angle A is greater than angle B. Angle A is greater than B. How can we prove this? So, you know our famous Euclid. Well, he has a great method that we are going to follow. So we are going to measure this side of our triangle, AC. And when we measure this side of our triangle, it is 1.5 inches. What I want to do is I want to measure the side BC, and I'm going to mark where 1.5 inches is with my pencil. And if I connected this spot to the corner of angle A, it also measures 1.5 inches. So I'm going to go ahead and copy that, and I'm going to trace this line with a red
marker so y'all can see that more easily. So now I have measured, this is 1.5, this is 1.5, and this is 1.5. So what kind of triangle is this? This is an equilateral triangle. So what we've done is we've created an equilateral triangle. So we know that this angle is congruent to this angle, and it is incongruent to this angle. Okay, so now we have an equilateral triangle inside of an isosceles triangle. So now we're gonna go through our rules and our proofs. So remember, our goal is to prove that angle A is greater than angle B. Have we already kind of shown that by making an equilateral triangle and seeing that angle A is greater than that? No, I don't think we've done it yet, but we're on our way. So now that we've redrawn that and you've learned how to redraw it, we're gonna actually just be going through the book now. So, looking at our first proof, it says, triangle ABC with BC line segment is greater than AC. Okay, let's see if that is true. Yes, angle BC, or line BC, is greater than line AC. You see that, how it's longer? And we know that because we have our equilateral triangle ticks, and we know that it would be equal here, but now it is longer. So therefore, this line segment is longer than this line segment. And how do we know that? Well, it is given, but also number 2 says, choose D on line segment CB so that CD equals CA. So we have almost done that on our picture right here. The only thing that we need to change is we need to add the point D. There we go. Now, back to our book. It says, and the reason that we were able to do this and know that they were equals, we used a ruler to measure. So anytime you use a ruler to measure, and that's how you know, it's called the ruler postulate. It says draw line segment AD, and we know how to draw a line segment because 2 points determine a line. Done, we did that. Angle 1 is equal to angle 2. So let's go back and look at our book. It says this angle in our equilateral triangle is called angle 1, and this angle is called angle 2. And are they equal? Yes, because we know it's an equilateral triangle. So this is angle 1, and this is angle 2. And so let's see the reason they give us. How do we know that these points are equal, or these angles are equal? If 2 sides of a triangle are equal, the angles opposite them equal. So we had an equal lines, or equal sides, and so therefore the angles across from them were also equal. Then, angle CAB, so we're talking about the whole triangle now on that left side, equals angle 1 plus DAB. And this is because of the betweenness of rays theory. So let's look at that and make sure it's true. Yes, that is true. CAB, this entire big angle, is equal to CAD, angle 1, and DAB, this angle that we did not name. So we have 1 and this angle add to the total of CAB. Saying all these letters gets kind of tongue twisted. Okay, so we know that because the betweenness of rays theorem. Now, CAB is greater than the angle 1. Yes, that's true. We just talked about that. And we know that because of the whole is greater than part. That whole angle was not only angle 1, it had angle 1 plus our unknown or unnamed angle. Also, CAB is greater than angle 2. Yes, that's true. And how do we know that? Because of substitution. If it's greater than 1, then it's also greater than angle 2. And we know from up here that angle 1 and 2 are equal. So we're down here, angle 2 is greater than B. How do we know that? Well, the exterior angle of a triangle is greater than either. An exterior angle of a triangle is greater than either. So let's look at this. Back to our original angle. our original triangle, it said that CAB is greater than 2. So this is an equal side of triangle, right? So we know this is longer. And if this is longer, a longer side, and we know this CB is longer because this is this long and this is this long plus extra. And so this side would be across from a longer angle. So we know that angle A in total is longer or larger than angle B because it is across from a shorter side. So a shorter side, a smaller angle. A longer side, a larger angle. So that is how we know that this is true. Angle 2 is greater than angle B. So because of the sides and the angle ratios. And then so lastly, angle CAB is greater than angle B. And we know this because of the transitive property. If this, then that, and then we have our conclusion. That's the transitive property. So this is this explanation of Euclid's proofs. We will have to do this in our homework, so I just wanted to make sure we went over this clearly.
Okay, let's keep going. You are awesome, and if you have any questions, send me an email or talk to me in class. Bye, y'all.